Okay, so welcome to the fourth lecture of second week. So in the last lecture, we were discussing about spelling correction and also seeing how do we do that with using the context. And remember the last problem that we are facing is how do we find the probability of a sequence of words? Okay, so I have a sequence of words in my sentence that might be a candidate. What the probability of that sequence? And that's why we said we will be using language models for that. So today the topic of this lecture is to see what are my n-gram language models, and we will start with some motivation of what are the different applications where we might need them. So n-gram language modeling is a very nice technique in NLP, and it's applied in many different applications. It's one of the very basic concepts in NLP. Okay, so let us see what are my n-gram language models. Okay, so I'll start with the motivation of context-sensitive spelling correction. That was the topic of just the previous lecture. So suppose I'm having the sentence, the office is about 15 minutes from my house. Okay, so here you can clearly see that there's a spelling error. Minutes has been typed as minutes. But suppose the word minutes is also in my vocabulary. Okay, so suppose I see my vocabulary and I find that minuet is some sort of slow graceful trance. Okay, that was popular in 17th and 18th centuries. So this word is in my vocabulary. So now that means I cannot easily detect that this is the incorrect word by using some isolated word error correction. So I should be using the context for that. So what is the probability that? So I will try to use some sort of language model to say that the probability of this utterance about 15 minutes from is higher than the probability of the utterance about 15 minutes from. Okay, if you observe these two utterances, you can yourself see that first one should be more probable. But how do we formally define these probabilities, and what is the model that we use for that? And that's what we will be seeing in this language modeling. Okay, now, so what are some of the other applications where this is helpful? Remember one of the earlier slides in our last week, we were saying in the case of speech recognition, you face this problem that when we are uttering something, you have to transcribe that. Okay, so whenever I'm saying I saw a van, it might also sound like I saw of an. Okay, so among the two utterances, which one is more likely? So again, can I give some sort of probability value to each of these sequences and say that probability I saw a van is more probable than the other? Similarly, in machine translation, there is a problem of collocations, that certain words, even if they are correct translations, do not occur much in the language in the context of other words. Like if I have the word winds, and before that as an adjective I can put either high or large, because so for example I have in Hindi utterance tej hawaएं, and I want to translate that into English. Hawaएं will be winds. Now for tej, it might happen that both translations high and large are possible in English. Now among those, which one should I choose? And suppose from my corpus I can find this knowledge that high winds occur with more probability than large winds. So then I would say that high is a more probable translation than large. And there are other applications, spelling correction we have seen, and you might have to use that for generation. Whenever you have to generate sentences, again which particular generation has a higher probability. Okay. Another possible application that you might be using it in, say, Google search or other places, whenever you are trying to type something, they will predict what will be the next word. So whenever I'm saying, please turn off your cell, what will be the next one? You can predict probably phone, please turn off your cell phone. And your program does not probably compile or something. Okay, so given a sequence of words, how do I predict what is the next word that is going to come in this sentence? So that is my auto-completion task. That is used a lot in query auto-completion, or even when you're typing something in your SMS or all. You might have certain softwares that do that. So they also use the concept of language modeling. Okay, so these are also called the predictive text input systems. So given whatever you are typing, they will give choices on how do you complete it. What are the various possibilities by which you can complete? Okay, so given these applications in background, let us see what is my language model, what is the goal, what do we want to achieve. So we talked about this. In the previous lecture, we said I want to compute probability of W, that is, what is the probability of the sequence W1 to Wn? This is a sequence of words. What is the probability of the sequence? So this is one of the goals, compute the probability of a sentence or a sequence of words. Okay, pre-W. What is the other related task that we saw in prediction system? That given 3 words W1, W2, W3, what will be my W4? So probability of W4 given the 3 previous words. So probability of an upcoming word. Now, in general, any model that computes either of these, probability of a sequence or probability of a word given the previous utterances, is called a language model. Okay, so we will see language model using these definitions. Okay. So now how do I actually compute probability of this sequence? W means sequence of words here. So suppose from the examples that we were taking initially, I have the sequence about 15 minutes from. I want to compute the probability of the sequence. Now suppose I do not tell you anything else, what is the simplest model that you will apply to compute this probability? So you'll probably apply the chain rule of probability. Yes. Okay. So remember chain rule of probability. So it derives from conditional probabilities. Okay. So conditional probability you might remember. So that is, what is the probability of B given A? That is probability of the joint probability PAB divided by probability A. Now you can also use that to write in some other way. So you can say probability AB is probability B given A times probability A. Okay. And if you can do that for any number of words in my sentence, or in general any number of events in probability. So you can say probability A B C is probability A, probability B given A, probability C given AB, and you can keep on doing that for any numbers, and that is my chain rule of probability. Okay, so I can write PAB as PA times PB given A. In general, even if I have more variables, I can do the same chain rule of probabilities idea. And this is the general formulation. Probability x1 given xn is probability x1, probability x2 given x1, and so on, and probability xn given x1 to xn minus 1. So now, given this chain rule, now go back to our initial problem, probability of about 15 minutes from. So how do I write it? Using this chain rule of probabilities. Okay. So how will you write this probability? You will say this is same as probability of about times probability of 15 given about times probability minutes given about 15, probability from given about 15 minutes. So you can write it like that. Yes. Okay. Now suppose I even increase this to about 15 minutes from office, what will you do? Okay. And you will write it in terms of this probability also, probability office given about 15 minutes from. So now the question that comes is, fine, I can write it in terms of chain probability, chain rules. How do I actually compute these probabilities? Now what is probability of office given about 15 minutes from? That would be, in my corpus, how many times do I observe about 15 minutes from? Among those, how many times I observe office after that? Now, what is one particular problem you will face in doing it in this way? You might not have seen sufficient number of about 15 minutes from in the corpus. Suppose it occurred only once, it occurred with office. This probability will be 1. But it does not mean that only office can occur about this occurrence. And this problem becomes severe as you keep on going to the higher and higher number of words in the conditional. Okay. So So we will never see enough data for estimating each. So I cannot estimate easily what is the probability of office given about 15 minutes from. So that means this will not work as it is. So we will need to do certain simplifications. Okay. Now, so what is the simplifying assumption that we make? We say, okay, we can probably use only the previous word and forget about everything else. So I have to compute the probability of office given about 15 minutes from, and I say that is approximated by probability of office given from. I forget the other terms. Okay. So, or I can use the previous two words. So this can be written as probability of office given minutes and from. Okay. So this is a simplification that we are making. Why we are doing that? Because now it is easy to compute the probabilities. What are the words that come after from, and what fraction of times office comes after from. But it was not possible when I was taking condition on 4 previous words, because I was probably not seeing them enough in my data. So this helps us giving a better estimate of these probabilities. Okay. More formally, we can use kth order Markov model. Okay. So I have to compute the probability of the sequence W1 to Wn. By using chain rule, I write it as this: Wi given the previous I minus 1 words, multiply for all the words. Now, in kth order Markov model assumption, what I will do, I'll condition it only on the previous k words. So I will write probability Wi given W1 to Wi minus 1 as Wi given only the previous k words. Okay, so here you are using only 1 up to k previous words and not all the I minus 1 words. So this is kth order Markov model assumption. Okay, so we can do that for all the components in this product. Now, and that's how we will define our n-gram models. Okay, so if I take this particular probability office given about 15 minutes from, if I am using only the previous word, okay, that will be using a 2-gram language model. So in general, if I am using only n minus 1 words of prior context, I am defining an n-gram language model. Okay, so here, if I am not using any word from the context, 0 words from the context, this is a unigram language model, and it's equal to 1 here. If I am using 1 word from the context, then it's a bigram language model, and it's equal to 2. If I am taking two words from the context, it is a trigram language model, and it's equal to 3. Okay. Now, can you try to relate an n-gram language model with some kth order Markov assumption? In kth order Markov assumption, we were using k previous word. So if I am using k previous words, I have a k plus 1 gram language model. So I can say an n-gram language model is an n minus 1th order Markov model. Okay. In n-gram language model, I use n minus 1 words from the context. So this is the relation between an n-gram language model and an n minus 1 order Markov model. Now in general, we can extend it to trigrams. We are using 2 words from the context, 4 grams, 3 words from the context, or 5 grams, 4 words from the context. Okay, but in general, we cannot say that any n-gram will be sufficient model for the language. Why? Because language, we also see some long-term dependencies. So consider this sentence: the computer which I had just put in the machine room on the 5th floor crashed. Now what is the word on which the word crashed depends? Okay, if you will see here, the word crash depends on the word computer, but this cannot be captured by using 2 gram, 3 gram, 4 gram, 5 gram, 6 gram, and so on. So see, so you might have to go to 11, 12 grams, and that is probably not very advisable. So you must always know that any n-gram model is not a sufficient model of language, but it captures many word ordering related regularities. Okay. So in most of the applications, we can use simple n-gram model with n equal to 3 and we will get away with that. Okay. So now the question is, how do we estimate these n-gram probabilities from a corpus? So for that, the simple method of estimating these probabilities is by using some maximum likelihood estimate. Okay. So what is that? Suppose I have to compute the probability of wi given wi minus 1. So I will find out in my corpus how many times the word wi minus 1 occurred. Among those, what fraction of times wi occurs after that. Okay. Remember, we were doing it in one of the earlier slides in versatile actress whose. So how many times the word actress comes after versatile? What fraction of times? Same here. What is the fraction of times that the word wi occurs after wi minus 1? So this defines the probability distribution. After wi minus 1, each word in my vocabulary can come, and this will be a probability distribution. Okay. So in general, I can give a notation as of C instead of count. C wi minus 1 means number of times wi minus 1 occurred in my corpus, and so on. Now let's take an example and see how do we estimate these probabilities. So I have 3 sentences in this corpus. I am here, who am I, and I would like to know. And you also have some tokens of the start of the sentence and the end of the sentence. And you want to compute the bigram probability, wi given wi minus 1. So how will you do that? So suppose I want to compute all these probabilities. Probability of I coming at the start of the sentence. Probability of here coming at the probability of end of the sentence coming after here. Probability of wood coming after I, and so on. So how do I compute these probabilities? So let us take the first one, probability of I coming at the start of the sentence. So I will find out how many start of the sentences I have seen. Among those, what fraction of the times I occurred. So I have seen 3 start of the sentence. Out of those, twice I occurred. So this probability would be 2 by 3. Here, how many times I have seen here? 1. Okay. And among those, how many times the end of the sentence occurred? Also 1. This would be 1 by 1, and so on. Okay. So this is what I find: 2 by 3, 1, 1 by 3, 1 by 2, and 0. So this is easy. Given the corpus, you can find out the bigram probabilities by just doing the counts. Now this is some example from some restaurant corpus. So that had 9,000 plus sentences, and these some bigrams that were the numbers are given here. So can you see some regularities here? So I and I do not occur together much, okay, but I and want occur 827 times. So you are in a restaurant, after I you mostly say want. I want some sort of food. Okay. So I want is a bigram that occurs a lot in this data. What are the other bigrams that occurred a lot? Want to. I want to do something. Eat Chinese. Okay. Chinese food. Eat lunch. To spend. So all these are bigrams that occurred a lot. So this tells a lot about that corpus. So I am talking about a restaurant corpus where it's more about ordering some food and eating some specific kind of foods. Okay. Now suppose I have to compute the probability, bigram probability. What else do I need? I need the count, number of times this word occurs with another word, and I have to divide it by the unigram probability of the previous word. So suppose I give you the unigram counts also for all these words. Can you compute the bigram probabilities? Yes, it becomes quite easy. So now I just divide it by the number of times I occurs. So here, so number of times I and want occur together, divide by the number of times I occurs. So this gives me probability close to 0.33. So probability of want occurring after I is 0.33 from this corpus, and so on. I can compute for all the words in this corpus. Okay. So now, given a corpus, you should be confident now that how do I compute the bigram probabilities. Now suppose you have computed bigram probabilities from the corpus. Now can you use that to solve our initial problem, that is how do I find the probability of this sentence, this sequence of words. So I have the sentence here, start of the sentence, I want English food and end of the sentence. I want to find the probability of this sentence. So how do I use Bigram model to do that? I'll say, okay, this is probability of I given as, start of the sentence, times probability want given I, times probability English given want, and so on. Because I'm actually using the chain rule of probabilities, but I'm using an first order Markov assumption. Okay, so that gives me all these probabilities, and I multiply that, and that gives me the probability of this sentence as such. Okay, so if I use the previous probability, that will be roughly 0.000031. And now you can give me any sentence, and I can use my Bigram probabilities to find out the probability of the sentence. And I can solve all my problems of content sensitive spelling correction and other scenarios. So now, so from this corpus, what does the knowledge of n-gram represent? Okay, so these are some values. So what do you try to infer from there? So probability English given want is 0.0011, and probability Chinese given want is 0.0065. What does that tell? So if you see, that will tell that the Chinese food is 6 times more popular than the English food in from whatever data it was taken from. Okay, 2 given want is 0.66, so that is 2 occurs a lot in that corpus after want. I want to do something. Eat after 2 is again 0.28. It's mainly about eating to do something, and to eat occurs with 0.28 probability. Food given 2 is 0. That means the word food never occurs after 2, and that is something that talks about the language. In language, generally use a verb after 2. I want to do something, and here the food is a noun, so this will not occur in my data. Similarly, want given spent is 0. Again, some fact about language that 2 verbs generally do not occur simultaneously. Okay, and I given the start of the sentence 0.25 again gives some indication that most of the sentences start with I in that corpus. So mostly about I want to do something. So it started with I. So these n-grams might represent some knowledge about the language and the grammar as such, or about the particular data or domain that you are trying to build these from. And this is some idea that we can use for even modeling different domains in my data separately. I can build different language models for each domain. Okay, so we'll talk about this further. Okay, so now, so there are certain practical issues that you might have to be aware of, like when I'm doing this probability computation for a sentence, I'm actually doing multiplication of many probability values, and all of these might be very, very small. So if I simply do multiplication of probabilities, it might lead to some underflow, and this might just end up in getting a 0 values for all the probabilities. So it's better that you do everything in log space. In that way, you are simply adding them, and in any case, adding is an easier operation or more efficient operation than multiplication. So you are just storing the log of probabilities, and you are adding these logs. Okay, so you can, if you have to find out probabilities P1 times P2 times P3 times P4, if you convert in log space, that is nothing but log P1 plus log P2 plus log P3 and so on. So you can store the log values, and you can just add these. There is another problem of handling zeros. Okay, suppose in your utterance there is a particular bigram that you see that never occurred in your training data. So what would happen? You will give it a value of 0, but that will convert everything to 0. Okay, so you need to do something for that, and we will see that in the concept of smoothing. Okay, so there are some popular toolkits that are available. So SRI-LM is one popular toolkit, but there are many other toolkits that you can use for language modeling. Okay, you can also, if you want to use some large corpus data, you can try to use Google n-grams. So they are again available on this link, and there you will find out for each different n-gram what is the number of times they occurred in the corpus. Okay, so if you go to this link, you will find out there are huge number of token sentences and all. Okay, they give you unigrams, bigrams, trigrams, 4 grams and 5 grams. So what are some of the examples? So suppose I am seeing it after starting from serve as the. So the data will tell you serve as the inspector occurred 66 times in their corpus, serve as the inspiration occurred 3090 times, serve as the installation occurred 136 times, and so on. So this is a foreground that you find from the data. But you see these are only the counts. Now how will you use that to compute the probability of inspector given serve as the? So for that you will also need to use the trigram count of serve as the. So again this file is available. You can get this foreground data and trigram data and try to compute all the probability values. Okay. Now, so they also give a nice API by which you can visualize many interesting patterns in the usage of words. Okay. So because the data is divided across many different centuries, you can also plot it temporally. So what we are seeing here, suppose I give 3 different queries, Albert Einstein, Sherlock Holmes, and Frankenstein on Google Ngram Viewer. It tells me over the years what is the probability of these bigrams. So can you see something interesting here? So Sherlock Holmes became popular around 1885 and so on. Before that it was nearly 0. Frankenstein were probably there in the novels even before that. So even from 1800 you find the occurrence of Frankenstein. That keeps on increasing. Even 2000 it's much more than Albert Einstein and Sherlock Holmes. Albert Einstein started getting popular in their data around 1970s. So that's where the most of the discoveries happened and it came into the books, and at some point of time it became more popular than even Sherlock Holmes. Okay. So you can do nice sort of analysis of what kind of words came into the language or my data in what times and how the popularity changed over the years by using these kind of data. Okay. So today we gave only some intuition and what is language model, how do we compute that, and what we can use it for. There were some problems that we saw, that how do we handle zeros. Okay. So with zeros the whole probability of the utterance will go to 0 even if one of the component has a probability of 0. So how do we avoid that problem? How do we solve that problem? That's where the concept of smoothing will come into picture, and that's what we will cover in the next lecture.